Okay, hi everybody, good morning. Before I start, I just want to say it's been a real pleasure just to see everybody sharing what they're doing with Ventsim and talking with you. It's very inspiring as one of the developers to get an insight into what people are doing with the software. It's really gets a lot of ideas going for us, and yeah, real inspiration. And thank you for that. So I'm doing this talk now and another one after lunch, and in those talks I'm going to be presenting the new software, Ventsim 6. You'll be able to download that this afternoon. The official launch is the next presentation. You'll be able to download the software, install it, and then embark with us upon this, the sixth epoch of Ventsim design. For this presentation, I'm first going to present in the theme of the session a few of the heat and vehicle features that we've got in Ventsim 6. And then I'm also going to talk a little bit about something that's coming, that's on the way. So I'll be talking first about electric vehicles and heaters and coolers. As we've seen, this is an industry that's always changing, and the challenge for us in Ventsim is really to keep up. And so we've been working on a few features for electric vehicles and heaters and coolers. And then that last one there to come, dynamic heat simulations. So this is a question that has been coming up more and more the last few years, and indeed in the last presentation. Dynamic heat simulation, are there ways that we can improve that? So I'll close out the talk with that. So firstly, electric vehicles. We've added some features to the new version. Basically, we've created a new category of vehicles. So we've had diesel vehicles for a long time. Now we've got electric vehicles, and it's really treated in much the same way. So if you're used to setting up diesel vehicles in Ventsim, you should be fine setting up electric vehicles too. So basically in the summary there at the top right, you see we have electric vehicles as another category that turns up as a property, but also in your summary of your heat simulation. And in the presets, we've got that new column there, electric vehicle power. And similar to the diesel power specification, when you're configuring your electric vehicle, you put in here the rated power output, the work of the vehicle in that column. And in this case, we've got 350 kilowatts. And then if you go over to the left, you've got the utilization factor. So you have 0.3. So this means that on average your vehicle is working at 30% of its maximum power. Behind that, there are a few new settings. So this is really still a developing field. So this isn't really set in stone, but it's something that we're going to keep an eye on to see the way this goes. And what I'm talking about here really is the sort of heat that the electric vehicle produces. So the first setting is the vehicle efficiency. So in contrast to the diesel efficiency of around 35%, we've got a higher electric vehicle efficiency. This means your electric vehicle will produce heat in your model at a much lower rate than an equivalent diesel engine. And so that setting there takes account of that. And the next one is the electric vehicle latent heat factor, which we've got a default value of 50%. So when you burn diesel, one of the products of that combustion is water, and basically the water that comes from burning that diesel we put into the air of the heat simulation. There's another component to that, which is that from observation it's been observed that we actually get a lot more water going into the air from a diesel vehicle than the chemical equation for burning diesel suggests, and we think the thinking is that that's due to the wet environment that the vehicle is often operating in. churning up the road, that sort of thing. So a lot of water gets involved in that heat transfer process. And so something similar is going to happen for electric vehicles. Even though they give off sensible heat, there'll still be a lot of water involved. So we started off with a value of 50% for this. So what that's meaning is that half of the heat coming off your electric vehicle is going to come out as latent heat. And you might adjust that setting depending on the type of mine you're in, how wet it is. But as I said, nothing's set in stone there, and that's something that we're keeping an eye on. Craig presented earlier yesterday on fires. So this is something we've done a lot of work on as well. Now this is based on Craig's recent work on this. Basically, the main difference here is instead of combustion fuels like hydraulic oil, rubber and diesel that we put into our fire, we've added this new category, battery combustion, a new preset, which sits next to the combustion fuels. And one of the findings of Craig's work was that we're better off considering the fuel from a battery in terms of its energy capacity rather than its weight. So the big difference there with the combustion fuels is that you can see there in the column titles, everything is per kilowatt hour of energy rather than per weight. So what that means when you're setting up your fire is that you can go to your fire wizard here, and you can see on the top right, we basically, in that drop down on the left, we include both the batteries and the combustion fuels, and you just pick the one that you want to use. So if you go to pick a battery that you want to burn, it'll come up, see the unit changes on the right there, kilowatt hours, and you just enter in the energy capacity of your battery. And then, of course, in the graph there, we've got another axis now. So you've got the burn rate of fuel weight and a burn rate of energy capacity per hour. And the other new feature there is we've added hydrogen fluoride. So this is potentially a product of fire with a toxicity that we need to be concerned about, perhaps comparable to that of carbon monoxide. So we've added that to the software. So your battery can have a yield of hydrogen fluoride per unit of energy capacity. That means that when you run if you set up such a fire here for a battery vehicle and you run your fire simulation, you'll get hydrogen fluoride as one of the gases that you can inspect during your fire simulation. Heaters and coolers. So we introduced heaters and coolers in Ventsim 5.4, and it's really been something that's been growing slowly over time. So I'm going to present that now, and I'm also going to show a few things that we've added specifically for Ventsim 6. So the idea here with heaters and coolers, we're moving away from a simple fixed temperature to model a heater or a cooler, and we're trying to make these behave in the software much like we'd expect them, more like we'd expect them to in real life. So we have two categories of coolers. We can fix the refrigeration capacity or the discharge temperature. And heaters, we started off with indirect and direct heaters, and we've added electric and air-to-air exchanges. So I'll just go through these different options. So with the cooler, the first one, fixed refrigeration capacity. In this case, we set a refrigeration capacity of 5,000 kilowatts, and so that's just going to add 5,000 kilowatts of cooling power. And we've introduced another property here that you can configure, which is the minimum temperature. So with a cooling plant, it'll often have a minimum temperature that it can actually cool the air to. So you can enter that here as you can see below there, 15 degrees. So that means that this cooler is going to try adding 5,000 kilowatts, but if the temperature goes below 15 degrees, it's going to stop there. So you can see it's got an output refrigeration of 2,500 kilowatts. And the discharge temperature, this works in a slightly different way. You set your discharge temperature and it's going to add however much cooling power it needs to bring the temperature down to 15 degrees. But again, you can set a maximum capacity. In this case, we've set maximum capacity here of 5,000 kilowatts. So in this case, the cooler is trying to get to 15 degrees. It adds 5,000 and only gets to 17.6. So that's what it does. And it gives you this warning here saying your cooler has not quite done what you asked it to do. So some things we're thinking about with this still, we've been talking with some people about how your cooling plant will be set up to work at a particular flow rate. And so if your flow rate changes, it may have an effect on the cooler performance. And so that's something we're looking to bring in, some sort of setting to derate the cooler performance if you've got a different airflow. So that's something that we're looking into and trying to learn some more about. Heaters, we started off with direct and indirect. Direct means you're burning the fuel in the airstream before sending it down to stop your intake from icing over. Indirect, you're still burning fuel, but in an indirect manner and not putting that fuel in the airstream. So the only difference here really is the efficiency. The indirect one has a heat exchange, so it's going to be operating at 85% efficiency, 100% for the direct one. And we've also added a few small things here. The direct one is now the direct heater is having an effect during your diesel and gas simulations, so it's adding the contaminants. Electric heaters. So really this is, again, 100% efficiency and really doing exactly the same thing, bringing the temperature down up to 5 degrees in this case, but reporting to you, rather than the fuel use, the electricity usage. And also new in Ventsim 6 is we're having a go at modelling air-to-air heat exchangers. So this is really a very recent feature. It probably hasn't been tested that much, and we kind of want to get a bit more real-world experience with this one. So if you do have an air-to-air heat exchanger, we'd be keen to get your thoughts on how this one performs. So this heater is really in a different category to the other ones in that we're not setting a temperature that we're going to heat to, but rather we're pairing two different airways, an intake and an exhaust, and setting up a heat exchange between them. So if you think of these heat exchangers, there's a lot going on. There's a lot of heat transfer coefficients to consider. This is kind of a bit more of a brute tool in that basically we have this one parameter which we call the air-to-air heat exchange effectiveness. So it's going to produce a kilowattage of heat transfer per degree of difference in the airstreams. Now, if you have that number, great, you can add that in and then set it off. But if you don't, then we've added a calculator which you can launch from the edit form. Which basically, if you have an example of an air-to-air heat exchanger and you know your temperature is going in and out of the heated airstream and the cool airstream, then you can use this calculator to calculate an overall heat effectiveness of the heater. Okay, so basically you pair these up, work out your effectiveness, and then it's going to heat your intake with the reject heat from that exhaust. So should be able to set up situations like this. So we've got in red there an exhaust. Yeah. And I've got data boxes here showing the temperatures and also the energy content of the air. So you can see this one is cooling from 68.2 kilojoules per kilogram to 58.6. And I've paired this heater with this one over here. And that is the heat from this exhaust shaft is now hitting the air coming in here from 2.3 kilojoules per kilogram up to 8.8 kilojoules per kilogram. Okay, so that's heat from this shaft, from this exhaust, exchanging with the air coming in to this intake. It gets it up to 2 degrees, and then I've basically set up another burner. This is like a propane backup, which is then bringing it up to 5 degrees. So you'll be able to model this in your model and then also get an idea using something like the annual thermal flywheel, you know, how this performs at different times of the year. Okay, so the last thing I'm going to talk about in this presentation is some work we're doing on dynamic heat simulation. So I think we had a really good example of that just in the last talk, where the question was, you know, we've installed a new cooling plant. What's the effect? How quickly are we going to notice that effect? And that's actually a really hard question to answer. The reason for that is the rock strata heat. So I've got here a diagram on the right showing what we basically simplify our airways to model the rock strata heat. So we model it as a cylinder and then and basically work out that heat transfer through that surrounding rock mass. So what happens is that the rock stores up the heat during during hotter times, and cooler times it will release that heat again. And what that leads to is the rock behaving as a heat capacitor. So that capacitance will basically lead to variations being damped out and also a delay in changes from the surface, you know, travelling deeper in the mine. You can sort of see that in this graph here from a paper from George Danko a while ago. So you'd know that from your own experience underground, that the deeper you go, the further away from the surface you go, the less you know about changes in temperature happening at the surface, because they're basically damped out by this huge amount of rock mass. So this applies to both daily and annual variations in outside temperatures, and also to changes in underground operations. So if you change your heat sources underground, these things, the effects of these will be somewhat delayed. So the way we model this currently is with this equation here. So this is the one-dimensional radial heat conduction equation. That there is its mathematical representation. I've got a little tool here which I'll switch to show you what this looks like graphically. Is that going to work? Do I need to quit out of this? Yeah. Okay. So basically what I've set up here, you can see this graph at the top. I've got a graph of temperature on the y-axis, so and the red line is showing the temperature into the wall. So at the very left-hand side of that graph, I'm at the interface of the air with the rock. This is a freshly dug tunnel, so everything is at the VRT, which is currently 41.6 degrees. And I've got a blue dot here, which is giving me the temperature of the air. So let's say that this is some cooled air. Say it's 15 degrees. And I'll just set this off. So that's basically what happens over time. You got the rock very close to the air, cools very quickly, but then as you go across from the graph, just remember this is expanding radially, so there's an increasing amount of rock mass as you go out, so it cools more slowly. And then you can see on the bottom graph, that's showing the amount of heat coming off the rock. So very early when it's dug, there's lots of heat, and then it falls away very quickly, and then more slowly cools and keeps cooling. So the way we handle this currently in the heat simulation is with the Gibson function, which is basically a big simplification of this equation. So if you've got a situation in this graph here, you can see there's a line there for 10 years, the bottom one. That's giving you the heat in the wall after 10 years. The Gibson function will give you the critical information that you need to work out the rock strata heat from that profile. But there's a big assumption to it, which is that it assumes that you have a constant airflow and air temperature over the life of the tunnel. So that case there with 10 years, that's what you get if you kept the airflow and the temperature the same for 10 years, or at least the average value the same over 10 years, which is would be quite a feat if you did actually maintain that over 10 years. So if we want to model something different, so let's say we have a change. I'll go back to my little tool. So just say we want to shut down our cooling plant for some reason, or it has to get serviced or something. Maybe bump this back up to 30 degrees. You can see that there's a dynamic response, okay? And a time to which this adjusts. So that's something that's really hard to model currently with the Gibson function. So with the heat simulation, it's very hard to do that. Similarly, if you're interested in, say, the annual and the changes during the year. So if you actually are interested in how the different seasons affect the temperature. Oh, I'll run that a bit longer. That sort of thing is quite hard to model with Ventsim, with the heat simulation, because that variation is going to take some time to model. That's just catching up. And similarly, you can look at you might be interested in daily variations as well. So this is still in development, and I'm just careful because I haven't got a cancel button on this. So I don't want to run it too long. Okay. So if we're interested in those things, then we're really, it's quite hard to model. So you're probably thinking, but well, hang on, we've got the annual thermal flywheel tool, and also Ventfire, which is also modelling heat dynamically. So what we're doing for these is we're basically trying to shoehorn the Gibson function into these dynamic heat simulations. So this works well for some cases, not so well for others. So with Ventfire is basically calibrated for use over several hours, and it uses some, basically an assumption about the thickness of rock that the changes in heat will penetrate to. And that's been validated. That works really well. The annual thermal flywheel one, we've got some calibration factors we use for that. They work for a range of scenarios, but the feedback we've gotten and from a few people is that there are cases where it's probably not accurate enough to be useful. So there's definitely some room for improvement there. So the option with being explored is to basically add a finite difference solver to Ventsim to more directly model this equation. So what is that? Basically, we take the rock heat in we break up the rock into discrete. We discretize that distance into the rock and basically solve this equation on very small cells along that line, on which we can solve these equations, and then we basically get that true behaviour with time. And the stage we're up to on that is basically what I just showed you. So the tool I was showing you there, that's the finite difference solver that we've written to model this. And so as you can see, we can do a lot of stuff with that already. We can do sudden changes to conditions and model them. We can also look at daily and annual variations in temperature. So it's still early days yet, but the big challenge now is to basically apply it to a whole model. So what I showed you there is modelling one airway. And of course, a lot of the interesting phenomena happen from interactions between different airways. And so the next big challenge is really to extend this to a whole model. So what that means is that you'll basically be simulating having a separate little finite difference solver for every airway in the model. So that's it involves a lot of computation, and there's still a few challenges to work through to get that going and to get it sort of solving quick enough. But if we get this up and going, we'll be able to, there'll be a few benefits of that. We'll have a better annual and daily flywheel simulation, and we can look at these sort of questions I've listed here that are currently a bit hard to look at. So, for example, what's the effect of a fan shutting down on the heat, the effect of a cooling plant shutting down or indeed starting up? And also, what's the effect of a large change in operation? So if you imagine you've got a fleet of diesel vehicles running up and down a decline for many years, and you swap that out with something like maybe an electric fleet, or maybe you replace that work with that fleet is doing with a hoisting shaft, that's going to have a big change in the heat. And there'll be a transition from one state to the other. And knowing what that transition will look like is quite difficult to model at the moment. And then potentially in the future we could look at doing a more kind of complete whole of life heat simulation. So I'm thinking here of maybe having different stages and simulating the heat through the stages, but having that memory of what happened in earlier years be stored in the model, like a heat memory on the airways. And so it basically would lead to a more accurate simulation, but also basically a more accurate simulation that would take account of historical changes in conditions in the mine. Okay, that's it for me now. I'll be doing a more thorough presentation of Ventsim 6 after lunch. Yeah, thanks for your time now.
Very impressive, Martin. So, any questions? I assume there would be a few today.
Thank you, Martin. My question was, if you're opening the model that you've just created now in like a 5.8 version, what is there like a node that comes up that's something, you know, like you might not get the right values? Or like, for example, if you're simulating an electric vehicle, is it just excluded? Like, how are we, you know, going back and forth between versions since it opens up in the previous version?
Yeah, so, well, that's something to think about during development. So we know that there's going to be a transition from people going to old versions to new versions, and maybe back again as well, because we know that happens as well. So we think about backwards and forwards compatibility. So was that your question?
Well, so what happens right now? For example, if I put in an electric vehicle and I open it in a previous version that doesn't support an electric vehicle, is it just excluded when I open it?
Yeah, that will. So that's a new property of the heat moisture diesel preset, is the electric vehicle power. And so if you go back to a version before that was there, then it won't be accounted for.
Okay.
Yeah, but that's been there a while now. Like we added that in. Yeah, like.
And that's how I know about it, right? Like that if you don't know that it's in the version and you open it, it's just excluded.
Yeah.
Thanks.
If I may, just on this, unfortunately, you know, when we release a new version, you want to make sure that the old files can still be run on the new one, but making it backward compatible is very much impossible. Otherwise, we wouldn't be able to add anything else. So yeah, it's just one of those things that if you're using a new feature and try to load it in old version, all that things are gone. But it's the case currently with anything really, like the activity tracks, for example, in Ventsim. If you open it in a model that doesn't have activity track yet, well, it won't be accounted for. So it is something to keep in mind when you're using a version. You want to have everyone you're working with using the same version. Darryl, you had a question?
Yeah, thanks for the talk, Dr. Griffith. We talked about indirect and direct fired heaters. And like with indirect fired heaters, we have the benefit we can capture, right, the latent heat of vaporization in the combustion products. So we get more heat out of the fuel, right? Is there a setting that we can use both, like we can input either a lower heating value or higher heating value for natural gas, let's say?
Yep. So you pick a fuel basically. So that's one of the things you configure in the heater. So you set a temperature that it's aiming for, and then you pick a fuel, and then it works out the amount of fuel you use based on the heat of combustion and any products as well from the combustion. So that's something. So it's the same preset that's used in the fire simulation. So we just look up those fuels. Yeah.
Okay, next question.
On the heat load from the diesel equipment that you have there, and putting it in and using a utilization factor
Yep.
on the engine relative to the nameplate power, is there an option in there to use the fuel burn rate?
Not directly.
Okay.
So what we recommend, what we teach is that basically you can use a calculator. There's one in Ventsim where you enter in the fuel usage, litres per hour, and that'll give you what your actual power output is, and then you can, if you want, you can put that directly in, or you can then back calculate your utilization factor.
Okay, so you would have to back calculate that if you knew what the fuel burn rate was on your equipment. Okay.
Yeah.
Hi, doctor. How are you? When I open the library for the electrical vehicle, does it already have or comes with a preset output of hydrogen fluoride, or do I have to look it up with manufacturers?
Yeah, so we've added a preset there based on Craig's paper, which has basically a heat of combustion per unit of energy capacity and also the gas output. So there's a default battery combustion preset there that you can start with.
Yeah. Thank you.
I'm interested, if you it's a developing field, and so I think if you've got, I think we'd be interested to see how people go with it, and if they have if there's new data that comes up.
I think those presets, like most presets in Ventsim, as mentioned by John on the first day, are always a good starting point. But if you have better values, don't hesitate to use those.
For the heat loads for electric vehicles, I didn't see an option, and was it considered, regenerative braking. So energy stored in the electric vehicle. So doing an energy balance across that electric vehicle, Daryl and his team found that the heat coming off wasn't what you would expect if you did an energy balance. And I think the takeaway was, well, some of that energy is getting stored from regenerative means. Is that considered in the heat load?
Well, if you're, the first place I'd look for that is in your utilization factor. I mean, if you're driving around and braking and getting power back and putting that back into your battery, then you're going to use that power again later, and then maybe and it would get converted to heat later on, and so you'd use less power overall. So my feeling is that you would include that in the utilization factor, and I think typically we're seeing the utilization factors are maybe a little bit lower for electric vehicles than diesel vehicles. Yeah.
Thanks.
A question from me, I guess. Any considerations regarding tracks going up or down, especially on a decline with these two tramming routes? What's the best way to simulate that?
Are you talking there about vehicle speeds?
More about the heat generation?
Yeah, I mean that's a question that's come up. These vehicles behave differently going up and downhill. They'll use more or less energy, go at different speeds. You can sort of average that out somewhat, because if you're doing a steady state simulation, then if you know what the overall work of that vehicle is, then you can just use that. But I think there are features we have now where we start looking at that more dynamically, and it's definitely something on the to-do list where we maybe specify different speeds or different average work depending on if you're going up or down. The way you can get around that now is you can, if you really want to get into that detail, you could set up 2 different tracks already and put different vehicles on each one. But that's probably a little bit clunky. But it's definitely something we're looking at.
Yeah, just to comment on that last question, I guess, the estimation of output of any engine, I suppose, it's always been a bit of a point of contention, and there's lots of studies to suggest what that may or may not be. But with diesel equipment, we've found by far the best way is to measure the fuel usage. With electric machines, I don't see any reason we can't do the same thing. For example, if we've got an electric machine with a 300 kilowatt hour battery, and the battery is depleted in 3 hours, the average output of that machine is 100 kilowatts. And that can be used to help validate any sort of utilisation figure you might come up with. So ignoring any potential energy changes with hauling rocks up heights, that really is a pretty good value to start with.
Thank you, Greg.
Yep, I'd say so. I mean, yeah, any utilisation factor would consider things like regenerative braking and that sort of thing. Yeah, but so if you're looking at it at a steady state, that's going to be adequate. Yeah.
Someone else? No? Thanks, everyone. And thanks, Martin, for the presentation.
Yeah, thank you.